difficulties, but now we're ready to talk about some K-theory. Okay, so what I'm gonna do in this lecture is talk about basically the construction of the K-theory groups. So maybe just before we do that, some stuff about why you might care about K-theory. So I mean, the main points are really that it's an invariant for C-star algebras. So that means that if two C-star algebras are isomorphic, that implies that their K-theory groups will be isomorphic. But really, this is more useful conversely, or in the contrapositive, which is if the K-theory groups are not isomorphic, then you know that the C-star algebras are not isomorphic. Um, and it's a really powerful invariant for C-star algebras. In particular, it's used in the Elliott invariant, which completely classifies classifiable C-star algebras up to isomorphism. And basically what the Elliott invariant is it consists of the K0 group, the K1 group, and other information that mostly relates to K-theory. So basically what we're going to talk about in this lecture is the K0 group and the K1 group. So where we'll start is with the construction of the K0 group of, well, this is going to be sort of a technical point, but your C-star algebra has to be unital for this construction. If you have a non-unital C-star algebra, you use a slightly different construction that we'll talk about when the time comes. But the idea is that we're going to build a group out of the projections in our C-star algebra. So let me just recall, if you're working in B of H, the projections in B of H correspond exactly to orthogonal projection onto a closed subspace, which, then allows you to deconstruct your Hilbert space as a direct sum of the image of your projection and direct sum of the orthogonal complement of that. And so this is sort of a nice, I guess, geometric framework to think about as we're going to be thinking about projections. So the place that we start is with a equivalence relation on projection. So we'll say that two projections in A are what's called Murray von Neumann equivalent. Um, if there exists some other element V in your C-star algebra with V star V equals P, which is one of the projections, and VV star equals Q. And then we'll write P and Q are equivalent like that if they're Murray von Neumann equivalent. So a couple of things about this. So maybe like a remark. I remember this being a exercise kind of early on in the goals notes, but when you have some element V where V star V is a projection and VV star is a projection, necessarily V is a partial isometry. And we give names to P and Q relative to V. So P is the source projection, and Q is the range projection. And let's maybe do a nice, easy example just to get a feel for what Murray von Neumann equivalence of projections is. So let's work in, let's say, M2 of the complex numbers. then I can define two perfectly good projections. Let's start with the matrix P, which will be 1, 0, 0, 0, which is projection onto the x-axis. And then the other one we'll look at will be Q, and its entries will all be 1 over root 2. And what this matrix does is it projects onto the line y equals x. And these two projections are Murray von Neumann equivalent via the partial isometry, which is 1 over root 2, 1 over root 2 in the first column, zeros in the other column. So this is basically projecting the x-axis onto the line y equals x and collapsing the y-axis to 0. Okay. And something that's fun to play around with at this point is all of the rank 1 projections in M2 of C are Murray von Neumann equivalent. And you can kind of try to find, what's the right partial isometry that implements that. So maybe this is like check, but any rank 1 projection Q in M2 of C, we'll say it has it's Murray von Neumann equivalent to projection onto the x-axis. So they're all the same. For another example, in like a more, I don't know, just not finite dimensional C-star algebra, let's look at bounded operators on little L2 of the naturals. So a nice example here, I'm kind of assuming that people have seen this operator already, the unilateral shift. So let's define an operator called S from L2 to L2. And what it does is it takes a sequence and it just shifts everything 1 to the right and adds a 0 in the 0th position. Its adjoint is then the shift in the other direction. So it's going to take the sequence A0, A1, A2, da da da, and it's going to shift it to the left and cut off that A0 term. Then basically by the definition of Murray von Neumann equivalence, if I build, because this S and S star are partial isometries, if I build S star S and S S star, these are going to be Murray von Neumann equivalent. But what these two projections are, you can check, but S star S is the identity, and SS star, I'll write it like this, is going to take a sequence A0, A1, A2, da da da, and it's going to send the A0 term to 0 and just fix everything else. So it's projection onto an infinite dimensional subspace of little L2. So by definition, these two are Murray von Neumann equivalent. And they are, I guess, infinite rank projections. That's sort of the commonality there. And the sort of thing I want to draw your attention to that's the through line with these two examples is that really Murray von Neumann equivalence is kind of picking out the rank of our different projections, so the dimension of the image. And that's basically a theorem. So for any two projections, P and Q in B of H, say P is equivalent to Q if and only if the rank of P, which by that I mean the dimension of its image, is equal to the rank of Q. So Murray von Neumann equivalence is kind of picking out something that's very geometric, the dimension of the image, and it's equating all of those projections. And at this point, I'll say this theorem, like proving this theorem, is actually really, I think, a fun exercise. So just give you that to do. Um, Okay, so this is kind of how you want to think about Murray von Neumann equivalence. It's picking out the rank of projections in B of H. Now, if you're working in a different C-star algebra, maybe there's less of a geometric intuition, but this is hopefully still going to kind of ground you. And our goal at this point is going to be to use projections and Murray von Neumann equivalence to build a group that will hopefully be our K-theory group, our K0 group. So build group out of projections and Murray von Neumann equivalence. Now, there are like two roadblocks at this point to doing this. So we have two problems. The first problem is that if you try to add two projections, you don't always get a projection. So P plus Q, it's not always a projection. But if you want to have a group, you should have P plus Q being a projection. So like, for example, just have something concrete. If I add these two projections in M2 of C, I get 2, 0, 0, 0, which is not a projection. And on the other hand, there are two projections that I could add together and I could still get another projection. So projection onto the x-axis, projection onto the y-axis, those sum to the identity, which is also a projection. So sometimes you get a projection when you add two projections together, and sometimes you don't. So that's kind of the first problem or the first obstruction to constructing a group here. And the other problem is that there's often different projections that we want to think about as equivalent, but they kind of live in two different C-star algebras that are intimately related. So I'll say it like this. We want to think of the projection given by the matrix 1, 0, 0, 0, which lives in M2 of C. And this larger matrix, this 3 by 3, that's also going to be projection onto the x-axis, but lives in M3 of C. We want to think of these as equivalent. And really, the reason for that is because they project onto isomorphic subspaces. They have the same rank. Really, these projections behave in the same way, and the C-star algebras that they live in are very intimately related. Um, so, yeah, but these are in different algebras. And the fix that we're going to use that solves both of these problems sort of at the same time is we want to work over matrix amplifications of our C-star algebra. So we're going to work in Mn of A, which is going to be the set of all n by n matrices with entries in our C-star algebra A. And if you haven't seen this yet, it's naturally a C-star algebra with, I'll say the usual matrix operations. So component-wise addition, matrix multiplication, all of that. But then when you do any of those operations, your entries come from A, so then it's referring back to the operations from your C-star algebra. There's a norm on this thing that makes it a C-star algebra, and all of the technical details like work out, but they're not going to be particularly interesting for what we're going to do. So, but this is what we're going to do. We're going to work over matrix amplifications of our C-star algebra. And then we need to define a few new sets that we're going to work with. So for notation, I'm going to use P of A to be the set of projections in our C-star algebra A. Then we'll also write P sub n of A to be projections in the n by n matrices over A. And then we need one more, which we'll call P infinity. And this is going to be the union of all of the PNs. So this is going to be projections in any matrix amplification of A. And once we sort of move up to matrix amplifications, then these two problems get fixed, but we need to redefine or tweak a little bit our Murray von Neumann equivalence to work in these matrix amplifications. So let's say for two projections in P infinity of A, let's say P is an n by n matrix and Q is an m by m matrix. We're going to define an amplified version of Murray von Neumann equivalence, which now I'm going to call tilde 0 for the name of the equivalence relation. This is because it's going to define our K0 group. But we define this new equivalence relation to be P and Q are tilde 0 equivalent if and only if there exists some element V that's in the m by n matrices over A. So V is allowed to be like a rectangular matrix. It doesn't have to be square. But it's going to satisfy the same thing that we had with Murray von Neumann equivalence. So P has to be V star V, and Q has to be VV star. Then just a couple of notes. Looks like the orange looks good. This rectangular matrix is gonna solve, oh, you can still see it, so I'll say this solves problem 2. So this rectangular matrix implements a Murray von Neumann equivalence or an amplified Murray von Neumann equivalence between our 2 by 2 matrix here and our 3 by 3 matrix up here. So it solves problem 2. Now to solve the first problem, which is that when we add two matrices, we add two projections, we don't necessarily get a projection. What we're going to do is we're going to define a new addition on this set of projections, P infinity of A. So we also need to define an addition on P infinity of A by, we'll give it a special symbol, O plus, and say that P O plus Q is going to be, we're going to send it to a matrix that has P and Q on the diagonal. So it looks like my screen stopped casting. Let me see if I can fix this. Oh, okay. I'm so sorry about these issues. I really don't know why this is such an issue for my iPad. Last time I just did this, I like tried to reconnect using the meeting ID twice and that worked. So I'm just gonna cross my fingers. The other thing I can try to do is I think that screen mirroring might work if I plug my iPad in. So give me 1 second.
Yeah, once you hit, if you get your iPad plugged in and you hit share and then you go to the advanced tab under share, there should be an option to share your iPad via cable.
On my, oh, advanced options. Okay.
There you go. Yeah, I think that'll do it.
Wait, I see iPad via AirPlay video file.
I have an option via cable. I'm not sure, maybe I don't know why I'd have more options because I don't even have an iPad right now. Hmm.
You can try AirPlay. Let's just
Yeah,
see.
try it.
Okay, we'll see.
All right, now you need to go to your iPad, swipe on the top right. There should be an option to like,
Yeah, I've got the screen mirroring icon.
Something like Zoom should pop up on your screen mirroring thing. It's almost like the Zoom meeting should be an option for you to choose.
Yeah, on my iPad, it's just the list is completely blank. Okay.
May look really fast.
Yeah, I'm gonna try one other thing.
Here, iPads. Hmm.
I'm gonna try a different cable and see if that works.
Fortunately for PC, I think you might need like a third-party app. I didn't really think about this before, but so, you'd have to potentially download something from the store, some sort of receiver.
Ah, geez. Okay, I'm gonna just see one more time if I can join using the meeting ID. Yeah, this is so wacky.
I did just learn the share by cable is only a Mac feature. So, sorry.
Yep, yeah,
Okay.
that's the thing.
Well, the thing that's weird is that it was working and then it just decided to stop.
Yeah, it's so weird.
Yeah. Um, I'm just trying to troubleshoot a little
Yeah, no worries.
bit. Thanks. Wait, hold on. Okay, now let's see if I can try doing the
Try again.
AirPlay again. Oh my God.
Wait, it's
I
doing
see my
something.
option. Yes.
Yay.
So good. Okay. Um, oh, but now I'm like sideways. This is gonna be a little bit wonky. Okay, unfortunately, I think this means that you can't see as much of my screen, and I also can't see as much as of my own screen. So, uh,
Right now that you kind of zoomed out.
yeah, so this looks okay. Let me just move this a little bit so I have everything set up. Okay, I think we're back on it. Thank you for your patience. Um, I had to minimize the windows where you can see everybody. So if anyone like has a question, just yell at me. Um, but okay, I think we're back to it. So where were we? We were talking about how to define an addition on this matrix amplification, the projections over matrix amplifications of A. And the way that you do that is you stick your two projections on the diagonal of the matrix. So I guess, for example, the two projections that we saw earlier that we could not add previously and still get a projection, the way that you add them now is you put them on the diagonal of now a larger matrix. So instead of adding the two projections that were 2x2s and getting a 2x2, we get a 4x4, but at least it's a projection. And this is sort of the reason why we work over the matrix amplifications, in some sense, is it allows us to add projections and still get a projection, just in a larger matrix algebra over A. Okay. Now that we have our notion of addition and we have our amplified Murray-von Neumann equivalence, this makes P infinity of A modulo this equivalence relation tilde 0 into an abelian semigroup. Okay, maybe some checks that you could do at this point that are just kind of fun exercises with the idea of Murray-von Neumann equivalence are that this is in fact an abelian semigroup, so P direct sum Q is tilde 0 equivalent to Q direct sum P. And the other thing that's kind of helpful for you to think about what's going on in this semigroup coming from P infinity is that any projection P is tilde 0 equivalent to P plus basically any zero matrix. So this is going to be the zero matrix in Mn of A. So you can always take a projection in a lower matrix algebra, like a smaller one, and push it up into a larger matrix algebra by just adding zeros on the diagonal. And maybe some examples of what this semigroup looks like for different C-star algebras. Say for the complex numbers, remember way back to the theorem that we had that said that projections are determined by their rank. Well, now we're looking at projections in matrix algebras over the complex numbers. So we have lots and lots of different finite rank projections. And so we can actually make a isomorphism coming from this semigroup to, well, we can get projections of any rank for any natural number. So we're going to send, I'll call it the tilde 0 equivalence class of our projection to its rank. And the theorem that we had before gives that this is going to be an isomorphism. And I'll say this kind of similarly holds for not just the complex numbers, but also matrices over the complex numbers. This semigroup is isomorphic to the naturals. And it also holds for the compact operators, but that might be something that you need to convince yourself of. And I think that so Maggie will also touch on this tomorrow. Okay, so this is one example. Another nice example that we can do at this point is for bounded operators on an infinite dimensional Hilbert space. And again, using that theorem that Marie van Neumann equivalence of projection is the same as just picking out the rank of your projection. When we go from our semigroup, well, now we have all of the finite rank projections, but we also have infinite rank projections like the one that we built from the unilateral shift operator. So we actually have basically that the semigroup is isomorphic to the naturals union infinity, and the same map gives the isomorphism where you take the equivalence class of a projection and you send it to its rank. Okay, so we have a slightly larger semigroup coming from B of H. But now we're basically in exactly the spot we need to be to define the K0 group. So we define K0 of A to be what I'm going to denote by GR of our semigroup P infinity mod tilde 0. And what I'm trying to say here is we're going to do something called the group completion, or building the Grothendieck group. So this is called the Grothendieck group. And what the Grothendieck group is it takes an abelian semigroup and it produces an abelian group by formally adding inverses. So this makes an abelian group by formally adding inverses. The construction in general is kind of technical and maybe not super enlightening, but the way that you can think about it is that this is kind of similar to how you would make the integers from the naturals.
Do you mean like the rationals from, because you said inverses? Or wait, you mean additive inverses
Additive
in this case?
inverses.
Okay,
Yeah,
cool.
yeah, exactly. Yeah, good question though. Okay. So yeah, just like you can kind of think about the integers having just all the negatives, this Grothendieck group has all of the negatives of these equivalence classes of projections. Okay. So looking back at these two examples that we just had where we found these two semigroups, we can then compute the K0 group. So for example, the K0 group of the complex numbers, I'm going to also say that this is the K0 group of Mn of C and also the compacts just by that remark. Well, the semigroup that we had was the naturals up here. So its group completion or its Grothendieck group is going to be the integers. Okay, so we've just computed a bunch of K0 groups and we got the integers. For B of H, When you do the group completion of the semigroup that contains the infinity element, infinity is like an absorbing element, and it kind of sucks in all of the naturals and it collapses the group to just the trivial group 0. And the way that you kind of think about that is if I take the class of infinity and subtract off any sort of finite element, I'm going to still have infinity, but that means that any number just acts like 0. So all of the numbers behave like 0 in this group. So the K0 group of B of H is trivial. Okay. And the way, I guess the standard picture of our K0 group is as follows. So you can think of K0 as containing formal differences of these equivalence classes of projections. You're doing formal differences because of this group completion process that I sort of glossed over. But your projections are allowed to range over any projections P and Q in P infinity of A. Addition in this group is given by, you can add two equivalence classes by doing the direct sum of the constituent projections and then looking at that equivalence class. And then the 0 element in K0 is exactly the equivalence class of 0 in the C-star algebra. So that's kind of the group structure. I think for the sake of time, I'm going to sort of skip ahead a little bit since I had some technical difficulties, but this is sort of how you're going to think about K0. We've built a group out of these equivalence classes of projections over matrix amplifications of A. Now, for constructing the other K group, okay, so our construction for K0, I needed to restrict to A being unital. And it's not clear why that restriction was made at this point, but essentially it kind of messes up the homology theory aspect of K theory. If you try to use this definition that we did for non-unital C-star algebras. So if we have time at the end, I'm going to circle back and do the non-unital construction, but I want to talk about K1 and make sure we talk about K1. So just keep in mind that the construction that we just did for K0 is technically only for unital C-star algebras. For non-unital, it's not too much of a leap. It's just a little bit technical. But how we construct K1, and like I said, there's no extra restrictions on what A is. But this one, we're gonna make a group out of the unitaries. But if A is not unital, then it doesn't have unitaries. So we need to look at unitaries in the unitization. So the way that you construct K1 is going to really mirror what we did for K0. So we're going to define a few sets that we're going to work with. So we'll use the notation U of A tilde to be the set of unitaries in our unitization. We'll define UN of A tilde to be unitaries in the n by n matrices over our unitization. And then just like we did with projections, we're going to have a U infinity, which is going to be the union of all of these unitaries over these matrix amplifications. Okay. Now, this U infinity is going to play kind of the same role in constructing K1 that P infinity did for constructing K0. So The other ingredients that we need are going to be some notion of addition in this set and also an equivalence relation. So let's define direct sum on U infinity by doing the exact same thing that we did in P infinity. So U direct sum V is going to be this diagonal matrix with U and V on the diagonal. And this will still be a unitary. And then we can also define an equivalence relation, which now I'll call tilde 1 equivalence, where two unitaries U and V are equivalent. Let's give them sizes for their matrices since they're in matrix amplifications. So let's say U is in UN of A tilde, V is in U M of A tilde by, okay, let's say U and V are tilde 1 equivalent if and only if you can find some number K greater than M and N. So we need some larger matrix algebra. And that's what K is doing, is it's telling you how big of a matrix algebra you need. But you need there to be a path from U direct sum the identity matrix in the K minus, I think maybe it's K minus M to get you to the same one. To V direct sum the identity matrix in K minus M. I hope I have the sizes of the identity matrices
I
correct.
think you had it right before you direct some
Yeah.
onto K minus N.
Oh, duh, because it's like N plus K minus M. Yeah. Okay, thank you. And that path has to be in UK of A tilde. So, well, this is kind of technical. What it's saying is that there's a continuous path of unitaries. It has to stay in the unitaries. Between these two, these are the kind of appropriate matrix amplifications of our unitaries. Because if you want to move them into the same matrix algebra and still have unitaries, you have to add ones on the diagonal to get them into, the K by Ks. So, notably, this is homotopy equivalence is really what we're saying. Okay. Then we can now define at this point we can define K1, and K1 actually doesn't need to be turned into a group. If we take U infinity of our unitization, mod out by this amplified homotopy equivalence, that's already a group, and it is the K1 group. And the structure of the group is really similar. So addition is coming from this direct sum. The 0 element in K1 of A is the class of the unit in A tilde. And inverses are given by the equivalence class of the adjoint. Okay. And so that's kind of the group structure there. So K1 is built from unitaries and K0 is built from projections. And I'll give a quick example of this, well, computing some K1 groups. So K1 of the complex numbers, and actually K1 of the n by n matrices over C, and also K1 of B of H. These are all trivial, and the reason for that is because for each of these C-star algebras, the set of unitaries is path connected. So all of the unitaries are homotopy equivalent, which means that, we have the trivial group. Okay. I have a little bit more that I want to say is, can I go until like 1, or what's the protocol?
The next talk usually doesn't start until 15 past the hour. I will be here, but I can't speak for other people.
Okay. I'm gonna talk about the 6-term exact sequence, and I might just go into 1 and we'll see what else can get covered. Okay, so one of the defining parts about K-theory that makes it such a special homology theory is what's called Bott periodicity. And there's a lot in what Bott periodicity actually is, but what's kind of important for the narrative that I'm constructing is really that there are only 2 K groups. They are the K0 group and the K1 group that we have already defined. And there's ways that you could try to define like K2, K3, etc. But basically what Bott periodicity says is that if you try to define the higher K groups, all of the even ones are isomorphic to K0 and all of the odd ones are isomorphic to K1. So there's really only 2 distinct K groups. And there is, well, those 2 are related by a long exact sequence that really, because there's only 2 K groups, becomes a 6-term exact sequence. So for a short exact sequence of C-star algebras, so we have an ideal going into our C-star algebra A, and then the quotient. We get a 6-term exact sequence, which will look like K0 of the ideal going to K0 of our C-star algebra, and then K0 of the quotient. And then the way that this gets written is like this. We go then to K1 of the ideal, then going into K1 of our C-star algebra A, and then K1 of our quotient. And then it wraps back around. So if you're familiar with, any homology theories like for spaces or something like that, there's always a long exact sequence induced by a short exact sequence of this type. And, because we only have 2 K groups, well, normally the way the indexing would work is this would maybe go up to K2, but K2 is isomorphic to K0, so it just loops back around. Okay. I think that for the sake of time, I'm gonna end there. Sorry about all the technical difficulties. But yeah, I think I'm gonna stop the recording now, and then if there's questions, I'm happy to answer those.
Thanks, Rachel.